your presentation.
Okay, sure. So I cannot see, yeah, you're recording. Okay, so as Pierluigi said, this notebook is to support all this lecture about flexibility, feasibility, nodal operating envelopes. And we have a brief introduction here on why this is important, but I think Pierluigi gave a great lecture about why it's important to characterize this operational flexibility of distribution network and distributed energy resources aggregated. So what we're gonna do is, the scope of this notebook is this algorithm that the OPF-based approach to get to the nodal operating envelopes and flexibility maps is just the first step, as Pierluigi showed, minimizing and maximizing the P and Q. And to do so, we're gonna use an optimization model. I added this part here of the flow that Pierluigi presented, because that's gonna be a big part of this notebook. We're gonna introduce the data, and we're gonna carry out these first 4 steps, which is minimizing and maximizing P and Q into the upstream grid. So we're gonna import packages. You will remember that from the day 2, they are essentially the same packages. And we're gonna do these flexibility maps, or start building the flexibility maps for the toy example that Pierluigi presented. So to have if you remember the model that I presented for the ACOPF in day 2, this example is essentially the same. It's a 2-bus system. We have a reference node, that's the bus 0, and then we have bus 1. And P0 and Q0 is the values that we want to use to build the flexibility maps. So that way you can really relate what Stephen explained and this 2-bus example into how to actually get the operational flexibility of a distributed energy resource disaggregation. We have the battery, the load, and the generator are essentially their operation will be the power, the nodal power in bus 1, P1 and Q1. So just to what we're gonna do is to study different snapshots of the operation of this aggregation of resources with different objective functions to build the flexibility map. So the first thing that this notebook does is to build the optimization model. Just a reminder, here you have a reminder of what, and linking what we did in day 2 with this notebook. So we have P0, Q0, V1, and the current are variables, and the P0 and Q0 are the active and reactive power to the upstream grid, and that allows us to represent the flexibility. The main difference is that P1 and Q1 are now variables and depend on the device operation, which is also a new variable that we're taking into consideration in this optimization model. Well, new variables, and we're using the ACOPF model from the exercise 1. So if you have any doubt, you can refer to that exercise for more details on the formulation. We're adding thermal limits on the transformer, which we didn't have in that first exercise. And of course, we're adding those operational limits of VR as Pierluigi showed. So here is the optimization problem. And you can see clearly we're using a function because we're gonna need to call this model 4 times in this first step. And we can clearly see what model variables are taken from the ACOPF, from that original problem that I presented on Tuesday, and what are the new variables. Now P1 and Q1 are variables, and we have the operation of the battery, the generator, and the load, and we're putting the limits we're bounding the variables to its limits for the quadratic operation of the battery, for the generator minimum and maximum, and the load also including minimum and maximum to have that flexibility that Pierluigi showed before of a more flexible demand. Then we have the constraints, also the ones taken from the ACOPF, and the new constraints for this model, which are a quadratic thermal limits for the transformer, and the quadratic constraint of the battery. That's how we get this full PQ capability of the inverter, and the active and reactive power at the bus 1 is the sum of the operation of all devices. And An important thing is we cannot define an objective function at the moment because we're going to change it. So that's defined as an input of this function here. Okay, so now we have the optimization model we're going to use. The second step is to get the input data, this PQ capability of the 2DR that Pierluigi showed. We're just translating this into the same parameters that were input of the model here, and the demand data, which is also given, and you can vary it to test flexibility of the load if you wish. This notebook will be uploaded to Canvas, so you will be able to play with it. And then we have the network data, very similar to the one from day 2, where it's also more explained, and we're also including the thermal limit of the transformer to take into account thermal limits to calculate the flexibility maps. So now that we have all the inputs, we can actually start with the algorithm, and we're gonna just do this step, which is the third step of the notebook, but the first step really of the algorithm. So we're gonna start by creating objects to save the results, P0 and Q0, which will be the values that will help us or will allow us to build the flexibility maps. And we need to solve 4 optimization problems: maximize P0, minimize P0, maximize Q0, and minimize Q0. And of course, we're interested to have these values subject to thermal and voltage limits to get the nodal operating envelopes and to start building flexibility maps. In each step, what we're doing is defining the objective function. You can see that here in this first case, maximizing P0, this is the rule of the objective function, and the sense is maximize. Second step, solve the optimization problem. So we call that function that we created before, and we save P0 and Q0, and we save them in this array that we have created to keep saving the results. And essentially, we have to repeat this for all the remaining cases, just changing the objective function. So we do the 4 steps, and once we have finished all the optimizations required, in this first step is only 4 optimizations. We will see these 4 points that also Pierluigi has shown before, something similar of these 4 points, the first step that you get of the algorithm. And when we see this figure that Pierluigi showed before of the PQ full nodal operating envelope, we can see that the values that we have gotten are equivalent to the one. So we are in a good track to do the flexibility map. This is only the first step. And essentially with this notebook, you are able to characterize the different limit points in the flexibility maps and understand how to characterize operational flexibility that can be given to the upstream grid. And you really have all the information, the model, the network, and DR data to, if you want, go to the next steps. Also, Pierluigi has explained pretty well how to continue from here, and it will be very interesting if you try to finish it. And Pierluigi, I think if you want to give any conclusion or final point.
Yeah, thanks a lot, Carmen. That's great. So if you can stop sharing, please.
Yes.
And just to clarify that you will have access to notebook. So everyone will have access to his notebook. We will put it in Canvas. That just is not okay. Is not. This is the first notebook. There will be more notebooks, as you see. Actually, where you will see that there is something very interesting is coming. It's coming later. They will be made available in Canvas. They're not there yet, so we're just checking the last details. Just want to make sure that everything what we give you is running properly and all that. But you will have access to that. And by the way, let us know what your thoughts about these notebooks. If you like it, they can be improved and all that, because we're working a lot on this kind of things, also for not only for research, but really for teaching purposes, as in this case. So just to conclude, it's I hope that somehow sort of convince you in a way that the DR has got huge capabilities of providing flexibility, especially in transition towards a system where there would be more flexibility required. The traditional provided flexibility will no longer be there. We're still lacking a proper framework to really understand the flexibility of DR, and there are lots of projects. There are a few attendees from Europe. There's lots going on. So what we try to do here, particularly with this nodal operating envelope framework, is really to have a solid ground to even from a visual perspective, understand what this flexibility is, and then try to come up with a few metrics that could be represented as not operating envelopes that could be that could support this flexibility discussions. How to build it? There are different ways, and if you look at OPF methodologies, effectively, and there was also a question about that. My suggestion is anything that is properly capturing the physics of distribution networks can actually be used. So you should be a proper AC, full AC optical power flow, like in a linear form, a convex relaxation, for example, what Stephen presented, particularly second order comp programming, I think is particularly suitable because also it's easy to understand, and also in case you need to interact with industry. And then if you use some linearized power flows, just make sure that the operational system of active and reactive power constraints is being properly captured. But otherwise, pretty much everything that we have presented in this course is actually relevant to build this map. So this is really like, you can take all those tools and build these maps. And in fact, what Carmen just shown here is we have used the tool that we have developed for Stephen's lecture to actually show you how you could build this flexibility map. And that's it in terms of the first presentation. There's also some additional material that I put in the slide if you want to have a look. Now, what I would like to do is I would just like to move straight to the second block. We're a little bit late, but I'll try to speed up a little bit because now I think you're also understanding better this kind of approach. It was important for me that you would understand well the conceptual approach to flexibility that I'm trying to give you. And now that I hope it's like better understood, what I'm going to do here is to actually show you some more details about the flexibility that comes from sector coupling. So when instead of just electricity, you look at introductory electricity with other energy systems, how can you extract flexibility from that? So we move from sort of electricity only flexibility to multi-energy flexibility with this multi-energy distributed resources, and from a power node model that we use as a starting point to a multi-energy node concepts. And then the flexibility maps that I showed you for active and reactive power now will become flexibility maps across multiple energy vectors, particularly electricity and heat, and then a few other examples that will become more and more exciting as you will see. Most of this is coming from the recent paper that we wrote with Gianfranco Chico, where basically we developed the theory of the flexibility from distributed multi-energy systems. So same as we developed with Sharik in the other paper, the theory for flexibility for DR aggregation. And here we developed the theory with about flexibility of multi-energy aggregation effectively. But let's try to move on. And again, the context should be now clear, and when you look at all these different resources, you would actually recognize that many of these resources are actually associated to heating, to cooling, to transport, to future fuels like hydrogen. So per se, there's not really electricity, it's other energy sectors that now interface with electricity through the resources. For example, heat pump for production of heating and cooling and these kind of things. Now, it is in this context that we need to look at the fact that is not only about electricity. Going forward with decarbonization, even if we put so much emphasis on electricity, the big issues are elsewhere. So this is like Sankey diagram of the UK energy system. We'll see more Sankey diagrams later, but the Sankey diagram is basically a representation of the inputs and outputs, energy vectors, and in between there are all the energy transformations. So when you look at the Sankey diagram of the UK energy system, it's from a few years ago, but there's not much difference. So can you tell me, what is really representative, interesting that you see in this Sankey diagram? By the way, actually, before we start with that, the question is, the question or the point, there are three colors, and there is this kind of purple, green, and like pink. By the way, there is a little bit of a story here with these colors. I am obviously, I'm obviously or not, I'm Italian mother tongue, and I find it extraordinary that basically nobody knows the actual names of these colors, even in English. So I don't understand why anyone who's built this diagram, this effectively the most important diagram of a country, right? Why don't you create it with very simple colors that everyone could recognize? Because I'm thinking nobody. Certainly, if I was to give this lecture in Italian, we have no idea as to how to call these colors even in Italian. Forget English and my bad English. So that's why I say, this is kind of purple, this is kind of green, this kind of pinkish. Probably people are a little bit more literate than me would be able to call them. Anyway, these different colors. One is heat, one is electricity, and one is transport. So it's really the energy going to electricity, heat, and transport. So which one of these colors, these three colors here, is electricity, which one is heat, and which one is transport? And by the way, most of it is coming from fossil fuels, as you can see here at the inputs. Okay, so in the meantime, I'm learning that there is this teal as a color. I never heard that. Just to confirm, this. In 10 years I give this kind of it's kind of lectures. I had any kind of names for these colors. That's great. And someone commented the list. It looks pretty. Yes, I agree. Actually, there is a big promotion exercise in having some nice colors there. So back to technical questions here. Yes, what you really notice here is that this sort of what's as an executive decision, I decide to call this pink. So this pink or pinkish color is actually electricity. This kind of purple is heat, and this sort of greenish thing is transport. So as you can see, as some of you correctly highlighted, electricity is tiny, it's small. And then transport is massive, and heat is massive. Now, transport is all coming from oil, basically. Heat is all basically coming from gas, and electricity is largely coming from different sources, and only recently we started having more and more wind and solar in the system. And this is for the UK. In many parts of Europe, it's similar. In other parts of the world, it's actually much worse potentially. So this to say that as much as we're interested and compelled actually by the fact that we need to decarbonize the electricity system, the big challenges are on heating and transport. So heating and transport together, they are about 80% of share of the final demand in the UK. They're basically based on fossil fuels, right? And so these are the technical challenges. I mean, when I was in Imperial College, when I was there as a researcher, my job was actually to work on decarbonization of heating. This was I started in 2008 there. I mean, if you're from the UK, if you know what's happening in the UK, we're still discussing about decarbonizing heating after almost 15 years. This tells you the challenge of even creating a framework, like in research terms, and then moving on with government action and so on to decarbonize the whole energy system, including heating that is largely gas-based. It is not only a technical challenge, it's a commercial challenge. How do you say to the gas industry, oh, we don't need you, or no, of course, to the whole industry? There are big real world challenges in there. So when you look at this kind of diagram, you understand why we talk about multi-energy systems, because now it's in the integration of the energy systems that it's in their decarbonization through integration that the future lies. And also the fact when we talk about electrification of heating and transport, it's all coming from this kind of diagram, because if you look at this diagram, you realize that if you know how to decarbonize electricity, then if you can electrify heating and transport, then you say, at least I can try to decarbonize the other sectors by coupling them with electricity. Otherwise, I would just not know how to do it. Only recently, actually, is a development in terms of hydrogen, for example. Again, that is really motivated by this kind of diagram. How do I decarbonize heating potentially and some part of transport and all that? Now, does it work or not? This is a different story, because you need to do all the techno-economic assessments and the massive infrastructure changes that you will need. However, the motivation to do that is really here. It's very significant and tangible. So when you look at this, effectively, then you say it's not only about electricity, but electricity plays a key role because it interacts with these other energy vectors and energy systems. So it is in this context that the concept of multi-energy systems was introduced some time ago, just to say, physically the system is multi-energy, but do we really model it and optimize it and everything else, like an integrated system? Well, not really. So what is that we need to actually move in this direction? And there are like, I was invited actually to write this paper now many years ago, really trying to present this multi-energy system concept that was very in its infancy at the time. Now, obviously, it's become very, very important. And this, again, this multi-energy system is a complete scalable concept, because a building is a multi-energy system. A community, a neighborhood, a city, a region, of course, a country is multi-energy. So it's all about seeing it as an integration of systems and sectors and everything else. Then how do we deal with that properly? When you look at this from the point of view of flexibility, again, we realize that everything that we said before in terms of flexible consumption demand side suddenly becomes true in terms of interfaces with the other energy systems. So what we call sector coupling is really electricity coupled to other energy sectors. And for us, in techno-economic terms, is become a multi-energy system, the way they want to model and optimize the system. So how do we interface with transport, with buildings, with heat, with cooling, with hydrogen in the future, and all that? So the modeling is based on this idea that, as we did before, there are basically aggregation of resources that now become multi-energy, and we have now distributed multi-energy systems that somehow are, again, multi-energy aggregates. And once I look at these multi-energy aggregates and the fact that the electricity is coupled physically, therefore could also be coupled operational in an intelligent way. So it's like really a smart energy system, not just a smart grid. How can I use this coupling to provide flexibility to the electricity system? And why would I use this coupling to provide flexibility? Because when you look at the mathematics, even from a mathematical perspective, what you do in electricity, there are a number of hard constraints in electricity operation, including the fact that you need to provide stability and then demand supply balance in active reactive power on a second or even sub-second basis. So when you look at different forms of stability, these requirements do not exist in other sectors. Basically, there's no other sector where you need to provide supply and demand balance, on a second by second basis. This is because there is intrinsic storage available in most of the other sectors, just because the physics of the other sectors is different. So you understand that having this kind of decoupling, this buffer, this storage available from other sectors can bring flexibility that is needed on the electricity system that is really subject to hard constraints in terms of operational system, including stability constraints. Now, from a sort of definition perspective, now you see that the same way as we define flexibility as the ability to shift operating points from a point of view of the electricity system, its aggregate. Now this shift can happen across multiple vectors, because I can now shift my operating point in terms of electricity, but also in terms of heat, or in terms of cooling, or in terms of transport, if I look at an aggregate where I am now providing multiple services. And then these points in particular, I can look at how much I want to shift my electricity operating point, but considering the fact that because electricity is now coupling to the other systems, by shifting the operating point electricity, I also affect somehow the operational point on the other systems. And the question is, can I do it in a simple way on the electricity system, and possibly in a cost-effective way, without really affecting what's happening in the other energy systems? Of course, I need a model to do this. And the same as we introduced the power node before, then what we do here is to discuss about so-called multi-edge node, because now all the equations that we wrote before in terms of one energy vector, electricity, actually power, we were only modeling active power in the original power node model formulation, here becomes completely multi-energy, in the sense that we can write the same equations in a vector, in a matrix form, where now you have multiple energy networks, vectors, and sectors in a way as an input and as an output. And then in between, there is conversion and storage. There's no longer just electricity as before, but it's also electricity, heat, cooling, transport, and they're all coupled. So mathematically, formally, actually, you can write the same or very similar equations as the power node in matrix form, where now the matrix is the multiple, it's an array of the multiple energy vectors, correspond to the array of the multi-energy vectors that you are considering. And for the mathematical details, I lead the mathematical details to the paper. However, it's really interesting also mathematically to see actually how this how you can create flexibility on the electricity system because of mathematically the different forms of coupling that you have. Because now you understand that if you have lots of different forms of coupling here, and you are interested in modulating, for example, if we assume that blue is the electricity system. If blue is the input and you want to modulate the input in terms of electrical power that is seen from this multi-energy aggregate, now, because there are different ways that you can transform potentially electricity into heat, into transport and all that, when you really look at this from a multi-energy perspective, including storage that is available, you have many more control variables in the system. And if you look at this from an optimization problem perspective, eventually you introduce degree of freedoms that enables flexibility. So effective flexibility is mathematical degree of freedoms in an optimization problem. Of course, it's an optimization problem. This is subject to constraints. What are these constraints? It's this multi-edge node constraints. It's still the physical constraints. And of course, there may be also some economic constraints. So that's why when we define this flexibility more specifically, we say the set of all feasible deviations in the flows of an energy vector, for example, electricity, from a given operating point, subject to the multi-edge node constraints. So I focus on one edge vector, electricity. Because this is associated to multiple decision variables in multi-energy system context, there are multiple degrees of freedom. Therefore, there is flexibility also mathematically. However, I need to constrain properly, and these equations are the constraints that I want to introduce in my aggregate, my multi-energy aggregate. Now I think you understand where I'm leading to, because effectively, if we go back to our beloved Minkowski summation, what we modeled before in terms of active and reactive power, and in a way, the electricity system is already sort of it's a bi-vector, in the sense that there's also this strange thing that we call the reactive power. Now, instead of reactive power, here we had heat or fuel. Effectively, you can build similar maps. The moment that you say that each sort of multi-energy device is actually characterized by a certain operating characteristic, operating map, looking at what is input and what is output, for example. So let's take the example of combined heat and power, whereby basically you have, for example, gas or hydrogen or diesel, whatever you want to have as an input. And then as an output, you have electricity, and then you heat that you recover in different ways, depending on the thermodynamic cycle that you use and the specific machine that you're using. If you look at the maps, then there are here different representations, because now there is a fuel as an input, and then there is electricity, active and reactive power, and also heat as an output. So I can create all these different relationships between inputs and outputs, but also between different inputs. Because, for example, now the active reactive power capability here is basically what I had before. It's, for example, a synchronous generator. This looks to be more like a synchronous generator than the model we used before. In this case, also, you see, we model this as a disjoint region where either you are zero or you switch on your engine, for example, and then you have a minimum stable duration level in terms of active power. But then, particularly interesting here is also how I model the relationship between active power and heat. Because effectively what I can do is, if I produce electricity, so if I move from minimum stable duration here for active power to producing more and more electricity, depending on the specific characteristic of your CHP, but in this case, I'm just assuming the heat grows linearly with how much electricity you produce, then you can move across this line here. However, if you can discharge heat, you can waste heat, it is also possible to basically move to basically operate in any of these operating points, because if I cannot waste heat, for example, for electricity output equal to 0.5, with the sort of assumptions I made here on the characteristics of this system, I would have to produce this much heat. However, if I can, for example, throw away heat, my operational point, for example, could be here. So same electricity, but half heat, because I assume that half of that I am throwing away. Now, it's never good to throw away heat, for you to be more about sort of combined heat and power and all that. However, if this is enabling flexibility, because again, it's adding a slack variable effectively to the optimization problem, then why not? However, this is just for a very simple example, but no, there are a number of devices that couple electricity systems. So the combined heat and power, of course, there is an auxiliary boiler that is coupling fuel to heat. There is an electric heat pump that is coupling electricity as an input to heat as an output. Lots of discussion about now power to gas, for example. Now, in this case, the electricity is the input, and hydrogen is the output. And in case after hydrogen, I can methanize and then have methane as an output. How do we represent these systems in a very simple way? So if you allow me to be very, very simplistic, basically, and say they're all characterized by linear characteristics, linear efficiencies, effectively, I can represent all of this in this kind of maps. Again, it's heat, fuel, fuel active power, heat active power. In this case, I'm not using reactive power for simplicity. And then you would see, for example, that when you look at the map that is linking active power and heat, if I take a power to gas characteristics, as you can see, basically there is no heat. I can change my electricity output, but the heat output doesn't change because basically there is no coupling with the heat system. However, if I look at fuel active power, as you can see, if I change my active power, I also change the fuel. In this case, fuel is negative because power to gas is producing fuel, it's not consuming fuel. If we go back to active power heat map, how do I model the electric heat pump? Well, effectively, as you can see here, if I basically consume electricity, in this case, so negative consumption indicates a negative sign for active power means consumption of electricity. In this case, I am producing heat. So there is a positive positive value for heat because I'm producing heat. And then you can do the same for the other technologies. For example, for combined heat and power, again, you see that I am producing active power at the same time I'm also producing heat. In this case, I'm assuming I'm not wasting any heat. So these linear relationships can be seen on the different maps in different ways. Now, what becomes very interesting is when we couple technologies, the same way as we coupled the different individual technologies for electricity, looking active and reactive power. Now we can look at all these different maps and we can couple technologies across these maps, again, by performing Minkowski summations in these different spaces. So when I do this, I can look, for example, at heat to fuel, fuel to active power, and heat to active power representations. And as you can see, I have now all these regions that I can create by coupling, for example, cogeneration, combined heat and power, and boiler, boiler and heat pump and combined heat and power. So very interestingly, when I look at these representations, there is very little flexibility here, or none at all, because basically what I'm saying here is, if I am producing active power, I also need to produce heat. If I am consuming electricity, I am producing heat for a heat pump. So where is the flexibility? How can I change operating points if I'm actually linked to moving just on that specific line? When I couple technologies, I'm no longer on a line. I have a region, so I can flexibly move in this region. So again, this is the magic of aggregation and the magic of the Minkowski sum to explain this. So I am actually creating flexibility here because I am coupling multi-energy technologies. And again, mathematically, you see that I have from two lines where basically there is no flexibility, I now create a region, and I now can play in different operating points inside a region. And I can do this across energy vectors. So that it's exactly sort of telling of the rationale of the multi-energy system. And again, now you understand that the more I couple, for example, I'm coupling here combined heat and power and auxiliary boiler and electric heat pump and power to gas, the more I couple, the more I grow in terms of flexibility. And then you have this kind of 3D representation. And I think now you start understanding more and more the magic. Distributed energy resources, because you couple them and because of the Minkowski summation of that, you create larger and larger operating space. Now the distributed energy resources are looking at the ability of extracting flexibility from interacting with other energy vectors. But if I am intelligent, I actually understand that if I can build a portfolio of multi-energy resources like I'm doing here, actually I can grow really immensely the operating regions that I have on a multi-energy space, and of course on the electricity system space. So now you understand that there are huge untapped resources from sector coupling that, again, we hear a lot about it. What I'm doing here is I'm showing you visually, and then in the paper you can also look at all the mathematics, why it is so. We can actually calculate and assess more than optimize with these equations all you want to do, from operating a system to design a portfolio of multi-energy distributed resources, having flexibility in mind from a technical perspective. But as we mentioned earlier, there are then metrics, can be cost metrics. And then, as I will show you in the last block, we can actually have market models for this distributed resources and flexibility. This is like part of the last block. As we've done before, there are also networks in here. How do I deal with networks in a multi-energy context? Well, networks obviously enable flexibility in first place. Why enable flexibility? Because if I have two resources that are sort of electricity heat resources, but I don't have, for example, a heat network that connects the two resources on the heat side, I cannot create any flexibility in terms of multi-energy interaction between electricity and heat, because these two heat resources are not coupled. So I need a heat network connection to create that. In the electricity system, this is there because all the resources are connected by the electricity system. So I didn't even bother saying you need an electricity system to connect it, because it's naturally there. But when we look at this from multi-energy perspective, resources can only be connected by the electricity system. For example, two heat pumps are only connected by electricity system, then producing locally heat. However, if I link the two heat pumps by a heat network, now I create the multi-energy map and multi-energy flexibility that I would need. So, of course, the connection enables the flexibility. At the same time, if this connection is small, I can actually have limitations of the flexibility I can extract, exactly as the constraints that we saw on the electricity side, for example, voltage and thermal constraints, were constraining my capability map into a feasibility map, and then all the other flexibility maps that we introduced. And then there are a number of other aspects. For example, in this paper we wrote some time ago, that now it's like it's very well read and cited. We showed clearly how the gas system can heavily constrain in the future the electricity system. The more and more you need the ramping requirements on the electricity system, the more the gas network needs to be flexible. However, for the ones of you familiar with the network, in the future, because the gas flows will change and all that, so will the line pack of the gas system. So I will show on the electricity system side that the ramps that we require through, for example, gas generators can actually be supported by the gas system with a very different line pack compared to what we have today. And that may not be the case. So just again, to give an example how you need to interact to couple the network models to really see the flexibility is available in the whole system context. Again, mathematically, you can see this because when you write the multi-energy node equations, because now you have constraints as an input and output on the multi-energy flows, because now you write these constraints and then these constraints are coupled by the multi-energy node equations, effectively you introduce constraints also on the electricity system, as well as, of course, on any kind of network that you can have. Again, you can just do it. You can see very quickly mathematically how this work. So again, the thing very similar to what we did on the electricity system, when we were looking at the very simple characterization of flexibility maps, like the feasibility maps, we could do it by hand, basically. The sort of vanilla Minkowski sum can be done by hand. That's actually how we did it the first times. Similar for multi-energy systems. The moment you have network constraints and network equations, unfortunately, you really need to go through some maths and introducing power flow equations. In this case, would be multi-energy power flow equations, which we will see in the next block very quickly. And then we shift from an electricity optimal power flow to a multi-energy optimal power flow, for example, gas and electricity OPF or electricity, heat and gas OPF, as again, I will mention very briefly in the next block. And just to give you some ideas of what I was mentioned earlier, I was saying, imagine you have two nodes here, a boiler here, an electric heat pump here. Of course, you have, in both cases, heat and electricity requirements at two nodes. Now, if I look at this from a perspective of there is no network, what I'm doing here is in each figure I'm going to show you, I'm increasing the heat network capacity from 0 to 1 per unit with respect to how much heat is needed by steps of 0, 0, 2. Now, if there is no heat network, so the capacity is equal to 0, these two regions in A and B in terms of heat and power are effectively two sort of disjointed regions. if I start increasing the capacity of the heat network, as you can see, the two regions, they grow in terms of flexibility in heat and power that is available in each node, because now I can transfer, because I can transfer some heat. This is equivalent to transfer some electricity flexibility from one node to another and the other way around. And then the more basically I grow in terms of capacity, I end up basically with a heat network that allows me full transfer of heat power from one node to another. Basically now the two systems are completely coupled, not only in terms of electricity, but also in terms of heat. And now I have a full multi-energy capability map available, and I can basically operate in any point in terms of electricity and heat power. And of course, there is this very convenient in economic terms, because while here I'm constrained in operating in terms of electricity and heat on given points on these two characteristics, now here I can basically operate on any characteristic, and I can, of course, from a cost perspective, try to optimize my system to operate under the conditions that are most convenient, effectively, for the system. So again, decoupled nodes, there is no flexibility, and then in here, the full coupled, there is full flexibility that is available. In terms of examples, there are several examples, and actually we will see this in great detail in next slide. So what we want to show here is very quickly one example where effectively you have flexibility coming from the fact that you have storage, thermal storage in a system. For example, you have a heat pump, thermal storage supply heat and power to my user. However, because the electric heat pump has got electricity as an input, by having a thermal storage buffer, you actually introduce flexibility by storage arbitrage on the electricity side. Even if it's a heat storage, actually you can introduce flexibility on the electricity side. Mathematically, it's seen from this kind of equation, the multi-energy node equation, where basically this storage here, S, in this case, it's heat. However, because there is a coupling here, H is the coupling matrix between electricity and well, in this case, H is coupling input and output, and is coupling then the electricity input to the heat output. So because of this sort of coupling that you see, effectively you enable flexibility on the electricity side. And again, what I would do here, I would pass the ball to Carmen. Maybe Carmen, if not, can take like maybe a little bit less than 10 minutes. And then after this, we have a bit of a longer break. We can breathe a little bit, and then we can we can go on with the rest of the lectures. So Carmen, if you can go on with your Jupyter notebook for this.
So thanks. I need to go up. So this Jupyter notebook is about buildings and energy, and why we're interested in modeling these buildings and optimizing the cost. Buildings are more complex because they don't want to deliver energy to the end user like a PV. That's not the main purpose. The main purpose is to provide energy service to the end users. When you're optimizing a building, you need to minimize costs, but taking into account user comfort. But by this kind of optimization problems, like the one that I'm showing now, oh, sorry, I didn't start my video. But these kind of problems like I'm showing now, we can take into account comfort while reducing costs. This means that energy demand of the customers is shifted to lower costs, lower prices, and this in turn helps the grid and the power system operation. So in this notebook, we're going to learn how to create and solve a simple building optimization problem using Payomo. This is the first time that we're gonna actually use time series data, and we're gonna show first a very simple example. And of course, if you want to learn more about these kind of models, you have this reference here. This is a very simple model. So we're first considering only the electric heat pump as a heating unit. And as Pierluigi said, to account for flexibility, we're also considering thermal energy storage, which affects positively and provides flexibility and makes a more efficient building operation. We're considering that domestic hot water and other electric house appliances are given, and we're modeling, like in our optimization model, we're considering space heating models, heating unit models, and the thermal energy storage. So here you have some sort of block diagram where the inputs, the models that we use, and the outputs. So we're considering environment such as external temperature and solar radiation, customer characteristics like their temperature preferences, and the building characteristics like heat transfer parameters, the thermal energy storage transfer parameters, and these all models in the end affect the electricity consumption of the building. So also in these heat problems, we use electrical analogs of the buildings and its heating system. And here you can see a complete electrical analogs of a building system, but also with the simplifications on this model, which are the heating unit is only the electric heat pump, the buffer model, so that part that allows flexibility is the thermal energy storage, domestic hot water is input data, we're not considering an emitter model, and we're reducing the building model to a one node model. So now we can start to actually implement this building optimization problem. We have to import packages, and we have a case study to provide us the data and to have the first results. This is a terrace house in Melbourne. We have 2 occupants of the house, and they have installed an electric heat pump. They have a temperature target they want to have when they are present and awake. This is 21 degrees. And we have building characteristics, resistance and capacitance for the one node model of the building. And we don't have electric heat pump, and the time series data for 1 day is provided in this CSV that of course will come along with in Canvas with this notebook. So we can see the data is import price, the solar gain, the air temperature. It's a very cold day in Melbourne, the electrical load, the domestic hot water load, and the carbon intensity of the grid. And we save those results, and we can save also how many periods we have using this notebook. And we also know how what is the time step, which in this case is half an hour. And we also need to save when the building is occupied to guarantee their comfort. We're also saving here in the second part of data input, the model parameters provided by the statement. And you have a brief explanation of each of them. And because we don't have a thermal energy storage, we put everything to 0. So now that we have all the input data, we can start building our optimization model in Pyomo. And a difference from the previous model is that we are actually using sets, which is it's a key way to model larger problems. So by using sets, we can model a variable like electricity import just with one variable for all the time steps of the optimization. And we're using that to have a scalable model. So the variables in this problem are the electricity import, temperature, energy level of the thermal storage, energy losses of the thermal storage, electric heat pump power, space heating delivered, and the heating to the building. And we're also considering this variable alpha. This is the ventilation that affects the exchange between the outside of the building and the inside. And there are much work trying to quantify appropriate limits and bounds of this variable. But in this simple problem that you just want to go to the concepts of the effect of flexibility by thermal energy storage and introduce building optimization, we're letting it change between 0 and 1 to avoid flexibility infeasibilities. Now the building constraints are here as follows, and we have also the equations for you to see how it translates the equation, the traditional written to code. We have this equation is to, or this constraint is to model the owner's comfort. This equation models the temperature evolution, the space heating provided. This is the heating provided by the thermal energy storage, the different gains with the outside internal gains and solar gains, temperature outside, the building characteristics. These next equations model the the thermal energy storage, and in this last equation, when X is the energy stored, and in this last equation, when we don't have thermal energy storage, we just have heat input, the space heating that goes to space heating delivered, and the domestic hot water. And the heat input, because we only have one heating unit, is defined by the electric heat pump here. The total electricity import of the house will be the power of the heat pump and the power demanded by other appliances like lights, computers, the fridge. And finally, once we have defined all the variables, all the constraints, we minimize the cost. Lambda is the price of electricity. And we solve this problem using LGPK, this solver. So by resolving solving this problem, we get the optimal cost for this day, taking into account users' comfort, which is $1.92. We can also find the total carbon emission, taking into account the grid carbon intensity, and we can visualize the results. So the first we can see how the temperature changes while during the day. So the first part of the day, the owners are asleep and it starts dropping the temperature. And before the owners wake up, the temperature increases and then stabilizes at 21 degrees while they are the building is occupied and the owners are awake, with small disturbances when the building is not occupied. So as we can see, because we have to have this increase of temperature, that's when we deliver the most space heating. And we can also see that the electric heat pump delivers almost all the heat in the building, and domestic hot water is not as relevant in this case because the domestic hot water load is minor compared to the space heating required. And we can also see the evolution. So in blue, we have the total energy demand. Then in dash is the electric heat pump demand. And then the other load, it's in green here. And we see how everything follows, everything is working well. And now we can move on to another exercise. In this exercise is following a similar concept to what we did in day 2. So in the previous notebook, we have presented the optimization problem. In this one, we're gonna focus more on compare exercises. So we're building a function with all the optimization problems. So we can call the optimization problem with only a few lines of code and compare different cases. So we have the same case. This first case, we have the electric heat pump. We just solve it. So I'm not gonna go through it. It's the same process. Now with only this line, we can call the optimization problem and get the results. And in this second part, we add the thermal energy storage. So we can see what is the positive effects of having a thermal energy storage and that extra flexibility. So by comparing the results, this thermal energy storage is providing an energy buffer, and we have less required space heat in the building, and this translates into cost. So because we have had, we require less demand, less heat input from the electric heat pump, this translates into a reduction of costs, which in turn translates into benefits for the power systems. Now, you have access to these 2 notebooks, and we recommend that you can try this example for 2 different cases. For example, if you have energy efficiency measures that increase the resistance of the building by 3, or with different objective functions, for example, minimizing CO2 emissions. And I have here as example, so it's the exact same case, but now I've increased the resistance of the building. And with those energy efficiency measures, we see that the space heat is reduced. So this is this new case. This is the case from the previous notebook. In both cases is reduced, but thermal energy storage and increased efficiency in the building are somewhat synergetic. So the reduction is even more pronounced in the case of when we have a thermal energy storage. So it's some sort of aggregating energy efficiency measures have an overall better result. And this can be seen also comparing the costs. So just a final comment is that this building optimization, we're assuming all the values known. So this means we're not taking into account uncertainty in, for example, demand, solar radiation, or occupation. So in reality, you should include uncertainty, and you can do so by solving this problem with a stochastic program with different values of these uncertain parameters, and see how the operation of the heat pump is affected. And that's the presentation of these notebooks. The first two notebooks will be shared in Canvas along with the data, the CSV data. And I will give it now to Pierluigi.
Thank you. Thanks, Carmen. It was very good. So I just wanted to add that in same way as you see that there is all this flexibility is coming from the adding a thermal store, and then of course by increasing the building resistance, which basically means, as we will see later, that's like a virtual storage model of the building. You can have the same effect. Say if you think of a demand response program, where effectively you are using electricity, and now you switch off the heat pump, and then because you got all this buffer, actually you are able to maintain for much longer the heat pump switched off. And this is actually what we're going to see next in next block, with where I will show you modeling of flexibility in buildings, and very quickly some ideas about when you have communities, how you model integrate communities, including including potential multiple energy vectors, but also some examples that are a bit closer to Australia, for example, community batteries. And then Alex will actually show you very, very powerful tool for this analysis of integrated energy systems. And then in the last part, in the fourth block, we will see all the sort of commercial integration, the market details, everything about this kind of how do we transfer this techno-economic flexibility into commercial flexibility in operation of distributed markets effectively. So this is coming next. However, I think we all deserve now about 20 minutes break. So it's 10:43 in Melbourne. So let's start again in let's say 22 minutes. So 11:05. We start again. In the meantime, I will read a little bit more questions, and yeah, I will try to answer some questions. Otherwise, I will address the questions in Canvas later on, as I said. So let's stop recording now, and I will see you all in 22 minutes.